this. So I've been at Push for the last 3 years, and as Rob said, before that I had a career consulting with BEA and with Oracle, and that took me in and around here quite a lot, so some of you may know my face. The Grinder is my open source project, so I don't know whether do any of you still use it, have heard of it, know what it is? No, that's pretty much what I expected. It was very much a tool of the last decade. It's about load testing synchronous interfaces, and nowadays, in today's event-driven world, it's sort of left on the shelf a little bit. So, anyway, on we go. This isn't a product pitch. What I'm going to do is actually expose the architecture of our key product, Diffusion, and sort of peel it apart and show how that architecture is specialized for high-performance broadcast. And it's a Java server, so hopefully that will be of interest to this audience. But in order to understand what I'm talking about, you need a little bit of context. So let me just tell you, very high level, who Push Technology are and what the products are about. So Push has been around for about a decade, and all we do is broadcast data over partly reliable networks, such as the internet. So we're not really a back-end system, although we are sometimes applied there. We're mostly about pushing over unreliable networks. Our main industries that we focus on are financial services and e-gaming. So if you using William Hill, you're seeing information that's being broadcast using Diffusion. And Diffusion is the flagship product. It's a Java server, runs in memory, and broadcasts data over a proprietary protocol that's layered on top of WebSockets. And we can fall back to polling using HTTP, so HTTP long polling if WebSockets isn't available. And although the server is Java, the clients are many and various. And in a typical Diffusion application, you have two types of client. You have the client which might be running on your mobile phone or hosted on a website, so running in a browser. And that's mostly receiving information. Mostly it's flashing lights and useful information to you. The other side of it, though, is that Diffusion needs information to broadcast. So we have a separate, typically have a separate class of clients which are pushing information into the server and creating the topics, which are the nodes through which the data is published, and also controlling the behavior of other sessions. So we have a rich control API that lets you authenticate sessions, monitor when sessions come and go, and pretty much control most of the behavior of sessions and topics from a client API remotely to the server. So for the first class of clients, you'd typically be using Android, OS X, or JavaScript. For the control clients, you might be using Java or C or .NET, or indeed JavaScript if you're deploying to Node. And you can mix and match. They surface the same capabilities, just through an idiomatic API. And then we offer the same technology in the cloud on IBM Bluemix and AppDirect, and that's under the name React. And all that's happening there is Push are taking the responsibility for hosting the servers, and you interact through the client APIs. So again, you can probably see why the control client API is kind of key to that offering. So anyway, that's the context. The two things that I want to talk about today, two subjects. Firstly, high-performance broadcast in Java. So this is sort of unpeeling the architecture of the server and the choices we've made in the server to achieve performance. And then the second topic builds upon that and looks at what publish and subscribe means to Diffusion, and it's a little different to other message-oriented middleware products, and how that then builds on the the high-performance architecture, so we don't suddenly throw away all the performance when we're trying to do quite complicated subscription processing. So high-performance broadcast. This is probably the bulk of the talk, and there's some little nuggets, so feel free to stop me as we go through if you have questions, so we're clear. So to whet your appetite, by high performance, we're talking about tens of millions of messages a second to high tens of thousands of connected clients from a single JVM, which is not trivial to achieve. And we have quite a specialized architecture in order to do that. Anybody know this face? This is the first of two heroes of mine that we'll meet in this slide. If some of you may recognize this face because I believe he spoke here last year. So this is Martin Thompson. You know Martin Thompson? Okay, right. So for those of you who don't, why am I putting him up here? I'm putting him up here for really for this phrase mechanical sympathy, and I'll explain what that means in a minute. But let me just say why you should know Martin Thompson. So he used to be CTO of LMAX. He was responsible for open sourcing and developing the Disruptor event passing library, which is a way of passing events very efficiently in Java between threads. He's worked on a messaging product recently, Aeron, which again is open source. It's a sort of back-end UDP, lightweight messaging transport. And he now does performance consulting and is really one of the most preeminent experts in Java high-performance, low-latency that there is. He runs a mechanical sympathy mailing list, and if you download the slides later, these are linked so you can link through to the Google group. There's some really excellent high-powered technical discussion there about mechanical sympathy. So what does mechanical sympathy mean? Well, Martin stole this phrase from Jackie Stewart, the Formula One racing driver. And when Jackie Stewart says mechanical sympathy, what he means is that a driver must have some knowledge of the mechanics of his vehicle, of how the transmission works, of how the brakes work, of how the engine is working, in order to get good performance out of his vehicle. And Martin translates that directly into software and says, okay, so if you're going to get better performance out of this hardware, you've got to know something about how it works, how it fits together. And that applies to many aspects of the hardware, but I'll just call out one so that it makes it a little bit more crystal here. If you think about a modern computer, they all have a cache hierarchy in front of main memory. So if you're running on a core and you want to read some information or write some information, and you can do that by accessing memory that's in information that's in your local cache, then you can do that very efficiently. If, on the other hand, you haven't read or written that cache line recently, or some other core has invalidated that cache, so you've had to throw away it, or you've been using other memory that doesn't fit in your other data that doesn't fit in your local cache, then you've got to go back through various levels of the cache hierarchy to actually access main memory. And the performance difference can be quite extreme. You can access things from local cache in a few nanoseconds. From main memory, it might take you 100. So there's two orders of magnitude there. Now, if you look at the Java specification, the JVM specification, or the language specification, neither of them say anything about this. They have this abstraction over it. You're just reading things from the heap. You're just writing to the heap. It's all the same cost. Well, it's not true. So this is one area where if you appreciate that and you write your software with that in mind, then you can get better performance benefits out of it. So this will sort of percolate through some of the things that I'm going to talk about. So let's switch over and talk about diffusion. And we're talking about broadcast, and the first thing I want to think about is how we want to assign one of the key resources that we have available to us, and that's the threads which fairly directly mapped through to the cores on the CPU. How do we want to allocate those for a broadcast problem? So one of the remarkable things about broadcast is it's quite asymmetric. If you're thinking about diffusion, where you've got some external client feeding events into the server, those events, those messages, are instructions that say things like, I want to update this topic, and then based on that topic, you might have 10,000 subscribers. So you've got one message coming in and 10,000 things going out. There's a complete misbalance between them. And that tells you without not too much thinking that you're going to need more threads, resources, dedicated to output processing, and that's what this little symbol means here. This is just this means a thread. And so here I've got a very simple machine. I've got perhaps 8 cores, and I've said, okay, I want to allocate most of them to output processing. And then we'll look at, well, what data are we moving around here? Well, when you're doing output processing, it's not if you think about what you actually got to do to send a message to 10,000 clients, say, that's not necessarily a simple problem because you've got 10,000 client sessions. They may or may not, at that point in time, have a live connection. So this is particularly true of diffusion. We're built for occasionally connected clients where the connection comes and goes, and connections can, a client can be disconnected and maintain its session, and then they come out the other side of the tunnel and reconnect, and we want the data to be flowing again. So you've got to deal with that when you're doing the output processing. You might also be getting back pressure from the network. So you might say, okay, I've got these messages to send to this client. I'll format up this buffer. I've got 100K to send to this buffer. I send it to the network. The network says, well, I've written 10K of it. I can't write the rest at the moment. You've got 90K in that buffer. You've got to do something with it. You've got to wait until I can write to it. You've got to do something else while you're waiting. You can't sit there and block. So the output processing is not necessarily a simple problem, but the state associated with that, you can partition up and you can say, okay, I've got 10,000 clients. Let's this guy be responsible for 2,000 of them, this be responsible for 2,000 of them, and so on. And then you've got a little world which you can work on in isolation of the other worlds. All this thread needs to do is sit there and process the output processing for those 2,000 sessions. Doesn't need to be worrying about the input processing or events coming from the network, push those to other threads. And I can just sit there in that box and just focus on processing those 2,000 sessions, and writing to those 2,000 sessions, dealing with those 2,000 connections just for output. So we've got two axes to this diagram. One is the split between input and output processing. And by the way, by splitting the input from the output processing, we get another benefit. It means we can concurrently be, for one session, we can concurrently be reading and writing information at the same time. We've got two different threads doing the processing. So we can have a sort of a truly event-driven flow. We can be receiving information and maybe publishing it at the same time information's going back in the other direction. So that's one axis, and then the other axis is this sharding or partitioning of sessions across the threads. And by creating this little world where I've only got to worry about 2,000 things, I can operate completely in isolation and zip through it. We'll return to this in a later slide, but we also have to deal with events that are coming from the network as well. So it's not just a sort of a flow of, I've got something to publish, okay, I make some change to a topic, and then I tell my output processors, go and broadcast this to the 2,000 sessions that you each have. But there's also events coming from the network that say, okay, this connection is ready to read, this connection is now ready to write, here's a new connection. So we're going to drill down into one of these, into the output processing now, and then we'll look at the network event processing. And it turns out that in diffusion, we found that the same pattern, same implementation pattern, suits both of them. And so to start off with, I'm just going to sort of describe the high-level pattern of how the processing flow works there. So this is it. I've called it the actor pattern. It's not the name we use internally, but it's probably the one that, if you're familiar with Acker or Erlang, then you can sort of see the similarities. And the main idea is we've got this little world. This is our output actor, if you will. One thread, pretty much mapping to one core. And in diffusion, we provision the server so that however many output processors you've got, you make sure that you've got at least as many cores so that you can dedicate a core to this processing. And it's working on local data structures. So that's data structures that only this thread reads and writes to. It doesn't, so they're completely private. So they don't need to be synchronized. They don't need to be concurrent data structures. This is the only thread that accesses them. And it goes through an event loop where it, first of all, pulls as many commands as it can about things it should do from a queue that's populated by upstream components, upstream threads. And it processes those, and by and large, those events can be completely, in fact, those events can be completely evaluated by their effect on local data structures. So very rapidly, we'll put a big batch of these things, and it very rapidly mutates these local data structures to reflect the commands that are coming in. And then because it's just not a box to generate heat, it needs to actually have some effect on the outside world, then it will do some output action. And then to actually get into the details of, well, what is that action, we need to look at an instance of this pattern. So the output processing, we'll look at that in the next slide. But say for the output processing, the output is writing the data to the connections. And then it'll just keep on going round in that little loop. And the most important thing here is that we've created ourselves a world where we can focus just on this state, just on this processing, without interacting with other threads, except for instructions about what things to do. So let's make that a little bit more specific and drill down into this problem for output processing. So this is the output actor. And the first question you've got to ask is, well, what's the state we're dealing with? Well, we've sort of touched on some of it already. Each session will have a connection of some sort associated with it. Think of it as a TCP connection, or a WebSocket connection, something that I can actually write data to. And for each session, we also have a queue of messages to format and write to that connection. So the first thing I need to be able to do as an output actor is to create that state. And so one of the commands that I'm going to accept from upstream is a S+. Create me a session. So I get a S+ coming in, create me a session. I create a message queue, just an in-memory local queue. And the command that says create me a session also tells me here's the connection that is associated with the session. I can process that completely without talking to any other thread. All I'm doing is just changing my local data structures. And by just working with these local data structures, and not talking to any other threads, I'm immediately making good use of the memory hierarchy of the local caches. Then we also have S- tear down sessions. I want to destroy some of this. But the interesting thing, the stuff that actually gets business done, is I want to send a message. And for the purposes of this slide, we'll look at a more complicated publication later on. But let's just say we want to send the message to all of the sessions. So how do I do that? I take the message and I put it on the back of each of these message queues. I want to send it to every session that I have connected. And in parallel, I've got the other 4 output processes in my example also doing the same thing. So yeah, I'm doing 2000 here, the other ones are doing 2002. But just in memory operations. And then when I've pulled as much as I can off this command queue, and Diffusion is very heavily biased to do that, it will take as much as it possibly can off this command queue and process and make these in-memory changes as fast as it can. Then I'm going to do some I.O. So I need to then pick a session that has messages to send. Well, in our example, they all have, because we're sending to everybody. A session, and that session has to be connected. So the connection that I've got is the session actually has to have a physical connection there established at that point in time. And I need to know that that connection is ready to write. So I haven't tried to write to it in the last cycle, or and been told that, oh, there's network back pressure, and had to wait for an event that tells me that this connection is now ready to write again. So there's a little bit of state around knowing whether I can write. But when I can write, what I do is I take as many messages as I can out of the message queue, format them into a network buffer, and pass them to the network. And then I go on to the next one. And the writes are relatively fast as well, because they're using asynchronous I.O. So the write won't block. It will write as much as it can, as much as the network stack will accept. If it can't write the full network buffer, then it will register with the network event thread to say, call me back when I can. And then, so one very quick operation, and then we're back into pulling things off the command queue. So we're getting very good batching here. Any questions? One question?
Using standard Java selector for the async I/O, or are you doing anything?
So we are, but the selector isn't here. So the selector is at the heart of the event processing. So I think it's 2 slides time, we'll look at how we actually interact with the selector. But it is standard Java async NIO. So we get some benefits out of applying this pattern. One of the key benefits isn't directly performance at all. It's that it makes it a tractable programming environment. It makes it something that a mere mortal can work with. You're not having to deal with concurrency issues. They're all upstream of you. You're dealing with very simple data structures. You can focus on optimizing those to match the problem that you're working with. You're not having to lock and so on. And there's no... the order is absolutely defined. So you're not fighting with other threads to get a consistent order of publication. You know that when you put that message in the back end of that local message queue, it will be coming off in the same order. There's no other thread trying to consume from that. And that will become more useful to us when we look at how we actually do publish and subscribe, and the complexity that then brings up. It's memory hierarchy friendly. So we keep these threads hot and spinning on the same cores, and they use thread-exclusive data structures that only that thread reads and writes to. So they're not constantly chatting on the caching, over the caching validation protocol. They're not constantly saying, oh, yeah, I've invalidated that cache line, and causing faults on other threads. So they can just focus directly on their own little world. It's parallel in sort of 2 directions. You can gain linear scalability across sessions by adding more cores, and you can immediately support, if you add n more cores, you can support n times more sessions. But also, it fits together as a pipeline. So we can be processing input while we're also processing concurrently output. And that too helps makes best use of the CPU resources that we have. So now we're going to look at the same pattern applied to Java and I/O. So we saw it on the first slide. We've got a network event thread. What's that doing? Well, that's essentially listening to events coming up from the NIO API. And if any of you programmed with the NIO API to do async I/O, you may have discovered some of the issues that are there in the API. What you're essentially doing with NIO is asking a selector to call you back when an event happens to a connection, and you give it a key associated with that connection, and the events are things like, there's data ready to be read on this connection. There's data, or if you say, if you know that the connection didn't fully accept the network buffer that you've written to, you can say, give me an event when I can now write to this connection, when the data that's pending for it has been written. And then the other key one that Diffusion needs to be worried about is, when a new connection request comes in to the server, that connection needs to be accepted, and that's an asynchronous process. You don't want to block the server waiting for that. You want to call back when the connection has been accepted. But the trap that the API gives you is that the selector or the set of keys that you've got waiting for events, changing that is not a thread-safe operation. And you have to either synchronize access to register or change that key set, which would then just bring the solution to its knees, because then you've got threads actually blocking on each other, competing over accessing this selector, or you apply the actor pattern and you use a single thread to deal with events coming from the selector, which is exactly what we do. The other thing I've got up here is just really about the nature of processing network traffic and trying to make sense of it. You really want to have a single thread processing messages coming off the network and a single thread writing to them, because you're turning data buffers into messages. You need to know where they begin and end. And particularly in diffusion, there's a defined order to those. You don't want to pull the messages off and then process them in parallel, because you want to maintain that order. So what we do, and this is sort of showing the threads fitting together a little bit more, we have a selector actor. So what's its state? Its state is mostly the key set associated with the selector. It's got a command queue, asynchronous commands coming from other threads. So one of the lines that's not shown on this diagram is the output actor, when it can't fully write to a connection, will be sending a command to the selector actor saying, tell me when I can write to this connection. But the commands here are things like register this connection to tell me when it's ready to read, register this connection to tell me when it's ready to write, or here's an incoming connection, tell me when it's fully accepted. Again, we pull as many of the things that we can off this queue as fast as we can. And what we're doing there is altering the key set, which we can do because we're the only thread doing it. We don't have to worry about thread safety. It's all good. There's a little twist to this, though, because it's not just the command queue that's input. It's network events that are coming from the selector. So as we pull things off the command queue, we actually poll the selector. We say, well, what else is happening? So the thread is still being kept hot. We're not blocking for this. And then the output of it, the effect that this has on the outside world, is essentially just scheduling work for other threads. So up here we've got write ready notifications, so that this can then say, oh, okay, I can now write to that connection, and I will consider it next time I go around my loop and next time I've got stuff to write. And then here we have the input thread pool, which doesn't use an actor. And it's sort of interesting to question, well, okay, so the actor pattern fits here, and the actor pattern fits here. Why doesn't it work for the input thread pool? good to sort of consider why. And there's three reasons. So the first reason is these have little worlds of state which are specific to them. So this has the selector, which it owns and can work with. This has the output processing for a shard of the sessions. This is dealing with more global state, and there's two big classes there. One is the topics that we're broadcasting to and updating, that they're shared, they're global to the server, and any input thread can mutate them. The control functions that we were talking about earlier can also alter the sessions. So so a control client can close other sessions or query what sessions exist or get notifications when sessions when the state of sessions change. So the set of sessions is also shared between the sessions, if that makes sense. And so that's reason number one, the global state that multiple threads, multiple input threads are working on. The second reason is that we have a server-side API where application code can be deployed and get callbacks from an input thread when certain things happen. And we just don't trust the application to play by the rules. So we don't want to make a sort of a critical high-performance part of the server be taken down by making calls to the application. So we actually do all of our calls to the application from here, the service deployed part of the application. And then the third thing is, mostly what diffusion is doing is broadcast. And as we sort of picked up from the first slide, all of the action about broadcast is over here in the output actor. So we don't, we can afford to dedicate threads to this and threads to this, but the ratio of input to output is heavily biased towards output. We don't need as many threads. We don't need threads constantly chewing cores here. So we can have more of a traditional thread pool. All of that being said, we do, where possible, where we know that a request is particularly associated with a session, we shard that, we stick it to a particular session, so we can use, we can do local optimizations and use non-thread safe data structures. So these are some results hot off our benchmark system, and I don't want to go into the real detail here. Just to sort of say, this is a benchmark special. We've got a mid-range server. It's quite old hardware now. It's a few years old, so you probably can't read that at the back, but that says it's a Xeon. It's 6-core and hyper-threaded, dual socket, so that gives us 24 cores to play with. And we're just using a commodity 10 gig network card. It's a benchmark special because actually the thing that's loading this doesn't have a real network in it at all. We have similar class injector machines all in the same rack, just trying to hammer the server just so we can focus on the server performance. This is part of our continued performance measurement. So every commit goes through this and we can spot regressions quite easily. So the thing I'd really like us to call out here, though, is the way the benchmark works. It starts off with a constant load, and I think it's something like it's a couple of hundred, or probably I think it's 500 messages a second across a range of topics. That's what's coming into the server, and we add subscribers. We add sessions that subscribe to all of those topics, and every few seconds we'll add another 100 sessions, add another 100 sessions, and that's sort of shown along this axis. And then this is the messages per second in millions of messages per second. And the remarkable thing about this is how linear the scalability is as we go up and to the right. And so even though you get a little bit noisy up here, that's probably the effect of good old garbage collection kicking in, and there's a little bit more pauses and a little bit more things sort of shifting in and out, so where you might lose on one calculation, you'll win the next time, so there's a little bit more noise there. It's still a linear progression. And so here, at the point where I put the latency chart up, we've got we're not near the top yet. We've got 60,000 connected sessions, so 60,000 60,000 connections, and we're doing 12 million messages a second. So yeah, that's pretty good. Over here, I'm showing the latency at that point. Now, we don't do anything particular in the server to monitor or manage latency, other than just really focus on this clean, don't touch other threads type. That principle carry that principle through the architecture. But we still get reasonable latency here. So here I've got a latency graph showing that the maximum latency that we're doing, the maximum latency is 130 milliseconds, and that's good. We're not an ultra high frequency trading platform. It's good enough for us. Okay, so having done all that work to partition the output processing into threads where they don't have to interact with other threads, it would be a shame if you then tied it in knots by tying it to the upstream source, to the input thread that's sending it commands. And the commands come in through a queue. We've seen the command queue. Unlike the message queues that you've got with messages to send, that command queue needs to be a concurrent queue. There are multiple threads writing to it and one thread reading from it. And you might look at the JDK alternatives there for a concurrent queue, which are really array blocking queue and concurrent linked queue, and they really don't cut it for a few reasons. So, firstly, they're concurrent, they work, they do the job, they fulfill the contract, but the main issue are performance issues. So with array blocking queue, when a producer puts something into a queue, it acquires a lock that's global, a single lock that's global to that queue, and the consumer is competing against the same lock. So only one thing can change that queue at the same time, and that dramatically brings down the performance. And with this, we'd be getting up to tens of thousands of messages a second, not to tens of millions. The other alternative, concurrent linked queue, performs much better, but has two fatal flaws. The first is it's a garbage generation factory. So every time you put something into that queue, it creates a node to change its internal structures, which costs allocation. So you might save one place, but then you'll just be paying it back by paying the garbage collector at the other end. And the other reason is that it's unbounded, and it's actually very hard to make bounded. If you start to say, oh, okay, well, I'll count how many things I'm putting into it and how many things I'm taking out of it, you then have to synchronize that. So what we need is a much faster in-memory queue. And for that, I'm going to bring in my second hero and see whether anyone recognizes Nitsan. Does anyone know Nitsan? So fewer, but still some people there. So Nitsan worked for us for 2 or 3 years, and actually a lot of the work that we've seen so far is Nitsan's work. He has a peculiar interest in lock-free queues, so queues that don't use traditional Java synchronization to work. And a lot of the development and his proving of these queues took place during the development of diffusion. He writes at length on these, and probably about half the blog at his blog, Psychomatic Lobotomy Saw, which is a most excellent. It's got a certain humour to it, but the technical content is just amazing, and the detail that he goes into benchmarking these queues is something to be seen. about half the blog is about these queues, but a lot of the work was came out of Diffusion, but now is available along with sort of enhancements that Nitsan has taken from other queues, so from C++ implementations and other academic research has all been piled into these very high quality Java implementations. And the good news is that they're now available under the Apache 2 license, so you can pick these things up and use them yourselves. Netflix have done that. Cassandra's done that. Netty has done that. So yeah, this technology is now sort of slowly spreading through the high performance Java servers. So the queue that we want from JC Tools, and the one that used to be in Diffusion but is now part of JC Tools, is called MPSC Array Queue. And I know I'm sort of getting close for 5 minutes. Okay, so I'm going to just actually probably skip some of the detail of this. I'll just call out the headlines. So MPSC Array Queue, one of the reasons it can be faster than the Java queue is that it doesn't need to support multiple consumers. It only supports a single consumer. If you try to use 2 threads and dequeue from this, then the guarantees that it's using will fail. The ground will fall from beneath your feet and you'll spin into the depths of hell or something. But it is a bounded queue. It shares some characteristics with the Java array blocking queue. But it's lock-free. It uses compare and set type operations in order to achieve the performance on the producer, and does something even more cunning on the consumer side. But I'll let Nitsan talk about that. So again, in the slides, there's links through to presentations that Nitsan has made around these queues. Right. In my last 5 minutes, I'm just going to try and charge through publish and subscribe, and what the problem is, and how we then build it into the architecture that we've seen so far. So, like other message-oriented middleware servers, Diffusion has a publish and subscribe model. So you have a hierarchy of topics, you're publishing data through those topics, subscribers that are interested in those topics subscribe to the topic and receive those updates. Unlike other message-oriented middleware, Diffusion PubSub is a little bit different. So firstly, it has a value-based API. We pass messages up to the application, not values up to the application, not messages. And what does that actually mean? Well, let me give you an example. So one of the key data types that the most popular data type with Diffusion is a JSON data type, where we've got a JSON document that's backed by a binary representation, an efficient binary representation of the document. And when the server receives a new version of a new value for a topic, it looks at the binary representation of the current value it has and the binary representation of the new value that it has, and it calculates the binary difference between them. And it sends the binary difference on the wire. And when the client receives that binary difference, it applies that to the old value that it has to create the new value, and it passes the value up to the application. So the application is dealing with JSON. It's got a rich composite data type. The messaging is dealing with tight binary differences, binary deltas, that means that you're not paying the tax for sending the keys every time if all you're doing is changing the values. Or if you're just changing one value, you're just sending that one value. So that's quite powerful, but implicit in that is, well, actually the server needs to know the value, needs to know the old value in order to be able to do this calculation. And most applications of Diffusion use stateful topics. So each topic actually has a value. That means that you can fetch the value, and I sometimes sort of characterize diffusion as a inverted data grid. So if you take an in-memory data grid like Coherence or Hazelcast, the way that they work, they're very much sort of put-get operations, request-response. I'm putting something or I'm querying something where you're going backwards and forwards to the server. They're not so good for the event-driven things. You can plug in a listener to say, tell me when this value changes, but that doesn't scale to having 10,000 listeners listening to a value changing. Diffusion's the other way around. We have some capability for query, but mostly it's about broadcast and, like I said, the inverted data grid. That creates a problem. You've got these values. When a new client subscribes to a topic, it needs to get the value before it can join the crowd and benefit from the deltas coming through. Then the third thing is with typical pub subsystems, subscriptions are a one-time thing. You say, I want to subscribe to this topic, I want to subscribe to this selector that matches a set of topics. That is an operation that resolves to a set of topics and you get subscribed and that's it. Diffusion actually remembers the selection that you've made, and as topics come and go, then subscriptions will get matched against those selections. Those selections persist. So that gets used quite a lot by our e-gaming customers. If you think about a subscription that says, I'm interested in Premier League football, then when Saturday comes and they set up a whole bunch of new events and new matches are created which map to new topics, all of those subscribers automatically get subscribed to those topics. And the alternative would be that the server would have to send out a broadcast to say, oh, I've just created a new event, and then all of the clients would have to say, oh, I want to subscribe to that, I want to subscribe to that, and so you'd have a big sort of administration storm around that changing. So I'm probably going to be cut short here. 5 minutes or no? Okay, right. So in which case, I'm going to leave it as an exercise to the reader to decode what's going on here and just cut short and say, any questions?